This will be our last section before your test. All right, chapter 5, first 3 sections, plus that last section of chapter 3 that we did on intro to functions. So this is just continuing that last section and going a little bit deeper into our content with polynomials. We're also going to look at some parent functions for graphs as well, and composition and combination of functions. So I have f of x represents this polynomial, this quadratic here, this beautiful, wonderful quadratic. And then I have f of negative 4. What does that negative 4 mean? X is negative 4. So what do I do with that negative 4 if I want to find f of negative 4? Plug it in. Okay? Plug it in. So f of negative 4 is negative 4 squared. Pay attention to that parentheses. 5 negative 4 minus, I don't know why this keeps going back. This is being finicky today. It's going to be that kind of a day. All right. What do I do first? Exponent. Okay. What's negative 4 squared? 16. And then I've got that negative out front that comes down. I can also do 5 times negative 4 to get what? Man, you guys are smart. Okay. Negative 16 minus 20. Minus 11. 47. Good. Yay! We got f of negative 4. What's common concerns? Alright. Next, word problem. Same thing. Function. But with a word problem. And they give us an equation. Alright? You got to parse out that important information and evaluate the equation and making sure you're plugging in the correct value of x. That's your biggest thing you need to focus on. What's the value of x that I need to plug in? Okay? We're still evaluating a function. They give you the equation. You don't have to write it. You just have to figure out what's the value of x you need to plug in. So we've got a number of U.S. households estimate to see what they pay at least one bill online each month during the years 2000 to 2006 can be modeled by that polynomial, where x equals 0 corresponds to the year 2000. X equals 1 corresponds to 2001, and so on. And then P of x, our function, evaluates to millions, okay, millions of people. Use the function to approximate the number of households that paid at least one bill online in 2006. So what am I going to be solving for? What's x going to be? 6. I need to make sure that I pick the right value of x. Since year 2000 is 0, 2001 is 1, I keep going in that pattern. 2006 is going to give me x equals 6. So we plug this in. 8086 squared plus 2625 times 6 plus 0.502. Now, I'm going to make a big assumption that you guys know how to plug into your calculators. I'm not going to take that 40 minutes. That's going to take you to do that. I'm pretty sure you guys can use calculator. Yeah, okay. So you'll evaluate that for whatever that is. I don't remember what it is when you come back to it later. Okay? All right. Combination and function composition. Profit is a function combination. We're doing a subtraction. So whenever you have a problem that represents profit, it's revenue minus the cost. So they're usually going to give you a function that models revenue. They'll give you another function that models cost. You'll have to evaluate those and subtract them, or subtract one function from the other. Profit is revenue minus cost. This goes into just our general adding and subtracting functions. These are different notations that you'll see and what they represent. So if you have f plus g of x, that's just adding the two different functions, f of x and g of x. And it's combining like terms. And then solving if you know what x is. Subtraction, f minus g of x. Again, you're subtracting those two functions. So if I have f of x is 3x squared plus 8x minus 6, and g of x is negative 4x squared plus 4x minus 8. F plus g of x, take f of x. So let me write it this way. Okay. finicky today. Don't do this. We take f of x and we add g of x. 3x squared plus 8x minus 6, and then we're going to add negative 4x squared plus 4x minus 8. Okay, I'm adding one function to the other. Do I have any distributive property that I have to worry about? No. What if I was doing subtraction? Yes. So you got to be very careful when you have that subtraction. When we do part B, you're going to have to distribute it. But here, since it's addition, I can just drop those parentheses. I don't need them for the addition. And then combining like terms. Give me some of my like terms. Good. So if I have 3x squared and negative 4x squared and I combine those, what do I get?
X squared.
Close.
Negative x squared.
Negative x squared. And, all right, any more?
Plus 12x.
8x, 4x, plus 12x. And anything else?
Yeah, 2. Oh, wait.
Negative 14. Okay, there's that combination. We added f of x and g of x.
And Barney colors.
You mean the color
Like
purple?
purple green.
Well, yeah.
It's like Barney.
Subtraction. Same thing, 3x squared plus 8x minus 6. But we're subtracting negative 4x squared plus 4x minus 8. So when I do that subtraction, what happens to that second polynomial?
Okay. Plus.
Yeah.
Plus 4x. Minus 4x. Plus 8.
Good. Distribute that negative all the way through. And then just combine that. 3x squared plus 4x squared. 8x minus 4x.
4x.
Negative 6 plus 8.
2.
Yeah. Add, subtract. Right. You've seen your seminar on Thursday.
What?
Alright, so a little bit more. We've got f plus g of x and we've got f plus g of negative 1. So f plus g still says, hey, let's add these two functions together. I need to find that part. And once I've done that, I also need to find f of g of negative 1, which means once I go ahead and do the combination, then I can substitute in the negative 1 and solve for that function. So f plus g of x is 18x squared minus 24x plus 3x, which is going to simplify to what?
Oh, 21. Square and then 21x.
There you go. Okay, so that's f plus g of x. That's f plus g of x. Now I need to do f plus g of 1. So what do I do with that negative 1? Plug it in. Okay, plug it in to f plus g. 18. There we go. Try that again. Once more with feeling. Plug in the negative 1 for the x, and the negative 1 again, and then evaluate. What's negative 1 squared?
So 1 and then 18.
Mm-hmm.
And then plus 21.
Mm-hmm.
Oh, and then 39.
There you go. So, combination, and then using it to evaluate once we know what x is.
So what's our final?
Yes, because it said find f plus g of x, that's f plus g of x, and f plus g of negative 1, which is 39. So it's both. Same thing with the subtraction. 18x squared minus 24x minus 3x. 18x squared minus 27x is the combination of f minus g of x. And then we want to sub in 1. this time for the solution instead of -1.
Sure.
18 times 1 squared minus 27 times 1. There you go.
So we put in the one with the x's?
The f minus g is that combination where we're combining the two functions. We get a new combination here. And then for f minus g of 1, we just plug in 1 for x and then simplify.
Is that it for today?
No. We also, for combination, have multiplication, division, but we'll cover that later when we do multiplication. We're just going to stick with addition, subtraction. But next thing we're going to do is composition. Okay, so combination is where we do the operations with our functions. Composition is where we combine the functions, input one function into another, is composition. So the biggest thing to note is the notation. Either way you'll see it. I'll often write it as the way on the right because it's a lot easier for me to type that into a computer. Is that nested notation with g of f of x. If you see g, this little looks like golf, okay? An O, but it's smaller. It's not multiplication. Not. Because we do have function multiplication. Okay? Function multiplication would be this. Function multiplication versus function composition. They do two different things. Function multiplication, we're going to multiply the functions together. But function composition, one function is the input into the other function. So when we substitute x with a number, if I have f of 1 and I'm substituting x with 1, if I have g of f of 1, I'm substituting x in my g function with the entire function of f. Okay? So one gets nested into the other. Alright? So I have f of x is x minus 4, and I have g of x is x squared. So f of g of x, f of g of x, g is my input into x. Okay, for my function of f. Alright? So, yeah. So what is g of x? X squared. So instead of having f of x, I have f of x squared. So everywhere I have an x in my function of f, I'm going to replace it with x squared. So here becomes x squared minus 4. I'm replacing variable with an entire function. Okay? If you can simplify, simplify it. If you can't, you can't. We've already got x squared minus 4. There's nothing else I can do to simplify it. There's no like terms to combine. So that is f of g of x. Okay? That's f of g of x. Now, f of g of 3. What am I going to do with that 3? Plug it in. F of g of 3. Whoopsies. F of g of 3. Get rid of that x. Nope. Do like that. You erased a second ago. F of g of 3, we're going to replace this x squared minus 4 with a 3 squared minus 4. Which gives me what? Plugging in that x with the number that's given and solve. Alright, so now we've got two different compositions here. We've got f of g of x, and then we've got f of g of 2, and we have g of f of x. So we've got them switched here, depending on what we want to do. Alright, so I've got f of g of 2, which means I need to compose g into f. I've still got f of g of x. Okay, what is g of x? What's g of x? Yeah. So I'm going to substitute x in with x to the power of 3 into my function for f. 3x cubed plus 6. Okay? said find f of g of 2, so now I need to replace x with 2. So f of g of 2, 3, 2 cubed plus 6. What's 2 cubed?
8.
Times 3 plus 6.
3.
Alright. G of f of x. F is now my input into g because that f is coming second. G of f of x. 3x plus 3 is my function f of x. 3x plus 6 is now going to be my input into g of x. So if g of x is x cubed, I'm replacing x with 3x plus 6 because f of x is 3x plus 6. F of x is my input into g. So the entire function of f of x replaces x on my function g. The entire thing gets put in. I just happen to have one term when I did it here for f of g of x, which makes it easier. But it's not always going to be one term. It could be 2, 3, 5. It could be 100 terms. Whatever x is in g gets replaced with this entire function. So g, f is the input into g. X on g gets replaced with f of x. Don't scoff at me.
That makes sense.
Better make it make sense.
Trying.
You stare at it long enough. Maybe
I
that'll
thought
help.
it would be, but my head's.
It's composition. You're talking about these circles? Yeah, it means composition. So the second function is the input into the other. So that's why I very purposefully write it. Okay, g of x is my input into f. So I say, okay, well, what is g of x? G of x is x cubed. So now I have f of x cubed. Whenever I have that input for notation, I replace my x value with what's there. So x became x cubed. Now when I have it switched, f of x was a little bit bigger. 2 terms. But those 2 terms are going to replace, not that one, but this x value with 3x plus 6. And that x value is being cubed, so that binomial has to be cubed.
How is that explained?
Say that one more time.
Like, I understand how we got the 3x.
Because x is cubed. X is cubed in g of x.
Well, why don't you just cube the
Because it's not distributed property. That does not at all equal, it does not equal 3x cubed plus whatever 6 cubed is, which is 200 something.
Oh, but I wouldn't cube 6.
No, you wouldn't.
I was just saying 3x cubed.
Nope. Because x is being cubed and x is 3x plus 6. X is that entire thing of 3x plus 6. So we plug it in. That entire function has to be cubed. And we're not going to expand it because we're doing multiplication next week. We're going to leave it just like that.
And the other one, after we cube everything, I use the 2 that was.
On the left?
Yeah.
So x cubed is going in for x. So it's replacing x. So that's why it's just the 3x plus 6. And then I want to know, well, x is 2. So now I'm going to plug in 2 for x to continue solving it and get down to 30. All right, so we're going to look at 4 different graphs. Okay, 3 parent functions. First is the identity function. It's a linear graph. Okay, the identity function is a linear graph. All right, straight line, passes through the origin. Any type of transformation will move that. So if I had f of x equals x plus 1, it's just going to take my graph and it's just going to move it up. Or if I had f of x, x minus 2, it's going to take my graph and it's going to move it down 2 units. A little bit more neatly. Okay, but it's still going to be a linear function. If I make the slope negative, it's going to go down instead of going up. This parent function called the identity function. It's a linear equation. A linear function. All linear functions have a domain of all real numbers and a range of all real numbers. All linear functions have a domain of negative infinity to infinity and a range of negative infinity to infinity. That is important key information about linear functions. Second, the squaring function, or quadratics. Okay, f of x equals x squared. They all have this same basic shape of a parabola. This extends to any even-powered exponent. They're going to have that shape, but as that exponent gets larger, this parabola just gets wider at the base. Same function, okay? Same general shape. They all have a domain of all real numbers. They all have a range that starts or ends at that vertex. The parent function goes from 0 to infinity. But if I make this negative, change the colors to red. If I change this to negative x squared, and now it's flipped upside down. Domain is still all real numbers, but the range is now changed to be negative infinity to 0. So wherever that vertex is, in whichever direction it's facing, is going to change where your domain and range is. Okay? But all of those even power exponents have that same pattern for domain and range. Cubic function. And this extends to all odd power exponents as well. Okay? And continues. 5, 7, 9, 11, 13. Okay? They're going to have this same pattern. Domain and range are going to be all real numbers. It's going to be this kind of sideways S type of graph. Domain and range, all real numbers. So it's important to know those so that when you get something similar, even if I had x cubed plus 3x squared minus 10, because this is a cubing function, domain and range is all real numbers. I don't have to know anything else about the function. All cubing functions will have this domain, no matter how complex it gets afterwards. If it is a power of 3, for the degree of the polynomial, it's going to look something like this. It's going to be in a different place. It's going to be moved around, but the domain and range is all real numbers. Okay? So if I want to graph negative x squared, okay, I can pick some values and I can plot these points, or you can use your graphing calculator and kind of look and see what those critical values are. Because it's a squaring function, I automatically know that my domain is what? Because all squaring functions have the same domain. All real numbers. All polynomials have that domain. Unless otherwise stated, if it is a polynomial, that is its domain. All real numbers. I can plug any value for x, and I can get a function. All right? Now, range. We just talked about the range on this one. What is the starting or ending point? Always start with the lowest value. What's the lowest value in my range? Negative infinity, because it's going down forever, right? So down forever, negative infinity, and it goes all the way up until what point? Bracket 0. Goes all the way up here. If I shifted it up, whoop. Yep. What would it be instead? Mm-hmm. If it was here. Always start with the lowest value. What's the lowest value? That's the lowest y value. Or that's not even the lowest y value. That's just, or the x value on the vertex. 1, infinity. So you just need to know where that vertex is to get your range. Domain is always all real numbers. All three of those have a domain of all real numbers. Easy peasy. Questions, comments, and concerns? Now we're done for the day.